Bismillahirrahmanirrahim. This video is from chapter number 8 of Mr. Alexander Sadiku's book, and this relates to a second degree equation, solution of a second degree equation. And here we'll be primarily discussing question number 8.17, and this is on the request of a student from Nigeria. Okay, before we start, just recall that there could be two scenarios. In one case, like here, when we close this switch, this voltage is applied across the capacitor and it passes through the inductor. So the capacitor will start charging, and the charging will be like this. Before the voltage was 0, then the charging will be gradually up to this is called 5 tau. Now this period is important for us. This we call transient period, and it is generally represented as t greater than 0. Now before this, the circuit was in stable condition, and after this also the circuit will be in stable condition, and which I call t greater than 0 or t infinity. What if the capacitor is already charged in the second scenario, and then we connect a switch? Then this capacitor will discharge through the resistances, and the discharge pattern will be something like this until it reaches 0. And this is also the transient period for t greater than 0, which is equal to 5 tau. So keep this in mind. Now coming on to the problem, the circuit in figure 8.71. The switch instantaneously moves from position A to B at t is equal to 0. Now this switch is connected to A and it is there for a long time. That means we can say this circuit is in steady state condition before t less than 0. Now I've just jotted down some points that I follow generally. We'll follow the sequence in solving this type of a question. Okay, but in this circuit we have to find the voltage Vt, voltage across the capacitor. Remember, in this book, the voltage Vt means the voltage across the capacitor. There are many books where they actually write Vct, which I think is a better option. Makes clear. Similarly, when we say IT, it means the current through the inductor is IT. It should have been ILT, but anyway, we'll follow what the book says. Okay, so we need to find IT first to find Vt, because the question says find Vt. So if we can find the IT current, that current at any time, when we say T, that means current at any time, and when we say Vt, then it is the voltage at any time. The general equation actually we have to find. Okay, and when we're saying that the circuit is, the switch is connected to A for a long time, for t less than 0, then two things happen. The inductor behaves like a short circuit, and the capacitor behaves like an open circuit. And the current at that time, we call it I0. Now, the first step of the strategy that we say that we have to find I0 and V0 first of all. At this point, we can find I0, and you can see this current, this is IT or I0. There is no path for this to complete the current flow, and therefore I0 is 0. No current will flow through this path. So we can write I0 is 0. Although current is flowing in this, but we are only concerned with this current, which is IT or I0. And what about V0? Now this voltage here is same as the voltage here. Some students have difficulty in understanding, but you can see there is no voltage drop in this or the whole path. So whatever is the voltage, same will be here, or whatever is the voltage here, same will appear at the output. So this voltage we can correct. We know the current, we know the resistance, and therefore V0 will be current multiplied by resistance, that is 60 volt. So these two parameters we have found for the t less than 0. We just note down, and then we move to the t greater than 0. The circuit is now moved into position B, and the current will now call it IT because it is in the transient state. We are in the transient time. That is, from here it is going down up to 5 tau. It will be in the transient period. So we are in the transient period, and in the transient period, the inductor will behave like an inductor. It will not behave like a short circuit. And similarly, the capacitor will not behave like a open circuit. So that is why we are writing it like this. And we need to find di0 dt, which will be used later in calculation. So how do we find that? Let's see. First of all, we write the KVL equation. Apply KVL around the right loop. So we'll apply KVL around this loop, and we can see if we take this direction, then R into I, then this L di dt, and plus Vt is equal to 0. This is for any time. And now if we want to find the value at t is equal to 0, then the IT will now be called I0. This Vt will now be called V0, and these two we have already calculated. And this circuit, since there is no source in this circuit, therefore this will be called source-free RLC circuit. And this is also called the second degree circuit because there are two energy sources. One is the inductor and the other is the capacitor. Okay, and this equation now will become, as shown here, at t is equal to 0, I will become I0. So plugging in, and Vt will become V0. And from here, just manipulating, we di0 dt, the rest moves on the right-hand side. So this is the equation that we will be using to find this value here. Let's plug in the values now. Minus sign, L is 0.25 Henry, R is 10, and then I0 is 0, V0 is 60. We have calculated here, so plug in that. That means di0 dt is minus 240. Now this is the value of di dt, minus 240. So we note down this also. And then we again at the transient period, if t is greater than 0, and if source is not present in this circuit, then the circuit is called source-free, as we mentioned already. This is a source-free circuit. Now in the book there are a couple of equations, and we have to select these three are for source-free RLC circuit. From these we have to select any one of the equations, and which one we select will depend on, let's see, this condition. If alpha is greater than omega, then we will select the first one. If alpha is equal to omega, we'll select the second one, and if alpha is less than omega, then we'll select the third one. Now what is alpha and omega? This is how it is defined. Alpha is R over 2L, and omega or omega naught is 1 over under root LC. So plugging in the values, we get alpha to be 20 and omega naught is equal to 10. So from here you can see that alpha is greater than omega. That means we are here, alpha is greater than omega. overdamped case. Therefore, we select this equation to solve. So we'll move with this equation now. So we have these values, di values, and the equation we know we have to use this. Now, and this is our circuit. Now there are four variables. S1 we don't know, S2 we don't know, alpha we don't know, alpha 1 and alpha 2. Let's find S1 and S2 first. This is the formula for S1 and S2. Okay, so plugging in the value alpha and omega, we get S1. These are the roots actually, roots of the equation. S1 and S2. From here, find S2 and plugging in into equation 1. This becomes our next equation. We call it equation 2. Now we have to find A1 and A2. So to find A1 and A2, the strategy we follow is put t is equal to 0 in equation 2. So let's put t is equal to 0 here. And put t is equal to 0. This will be I0. This will multiply by 0, 0. So we get I0, A1, A2. And this is our, let's call it equation number 3. And then we differentiate the equation number 2. So this equation we are differentiating with respect to t, and I hope you know how to differentiate. This value will come first, and this is the differential equation. And here also we'll put t is equal to 0 now. Putting t is equal to 0, we get this value. 0 will make it 1. So the final value is equation number 4. So we have equation 3 and equation 4. We know the value of I0 from here. We also know the value of di dt from here. So plugging in will find the values for these two. Now let's plug in the values. I1 is equal to 0. And from here, we get the relation that A2 is equal to minus A1. And the second one, we plug in di dt value in the second equation, this one, and this is the value. And here, now we can put the value of A2 is equal to minus 1, so putting minus 1. Now solving for A1, we get A1 to be minus 6.928. A1 found, A2 is just opposite of it, so A2 is minus A, that is 6 plus 6.928. Okay, so now we have these two values. This was our equation. Plugging in the value of A2 and A1 in this equation, this becomes our final equation, which we can rearrange and write in a neat manner. That is, we take 6.928 common, and then we get this value, the positive terms we are taking first, negative term at the end. So I hope you have been able to follow, but hold on, this is the only half part. We have calculated IT, but we need to find VT. The question says we have to find VT. Let's proceed. We know the equation of the voltage across capacitor is 1 over C integral IT dt plus some constant. And the constant is V0, which we have already calculated to be 60 volt. So, and IT, we got the general formula in the previous slide. So we plug in and integrate. So plug in the value of IT and the constant and integrate. We take 6.928 outside, this one, and this dividing will be 173.2. And now we separate the two terms, 173 and the first term, and then minus 173 and the second term, integral plus this constant 60. And we will use this formula. I hope you remember. Integral of EAX dx is 1 over EAX. So this one divided by the A of the power minus 37.32. And since this is a limit from 0 to t, so we'll be putting limit from 0 to 2. Both case. And we take the denominator out, both cases. Plugging in the values, so this will be t and this will be minus e. E is equal to 0. Similarly here. And we know E0 is 1 for this value. Okay, so we were here, and now we can open the bracket. So this will become 464, and this will become minus 64.65. So adding the constant, so we will get this answer. Now this is 0.01. This is due to rounding off error, I guess. So we will neglect this. And so the final value of Vt will be as shown here. And this is the answer that has been given in the solution manual. So we are getting same answer. So I hope you have been able to follow this. Please let me know through your comments.